Chapter 10. Emerging Trends and Future Directions. 10.1 The Impact of AI Research on Neural Network Evolution. The field of artificial intelligence, AI research, is integral to the ongoing evolution of neural network technology. Neural networks, which are computational models inspired by the biological neural networks of the brain, have been at the forefront of AI development. The ever-expanding capabilities of AI research influence the design, implementation, and functionality of neural networks. This section explores the profound connections between AI research advancements and the progression of neural network methodologies. AI research has introduced new frameworks for developing more complex and efficient neural networks. These frameworks, such as TensorFlow and PyTorch, provide researchers and developers with rich toolsets to innovate and implement neural network architectures. Advancements in these frameworks allow for the creation of deeper networks with increased layers, known as deep learning, which greatly enhance the model's ability to learn from large volumes of data. Furthermore, ongoing improvements in these frameworks have lowered the barrier to entry for AI practitioners, allowing for the democratization of AI and deep learning applications. One significant influence of AI research on neural networks is the concept of transfer learning. Transfer learning is a technique where a model developed for one task is reused as the starting point for a model on a second task. This approach affords neural networks a form of adaptive intelligence not unlike human learning processes. It helps in assisting smaller datasets and reduces computational resources by leveraging previously learned features from large datasets. Consequently, transfer learning has become a staple in modern neural network applications, leading to increased efficiency and broader applicability across different domains. Another trend driven by AI research is the progression towards explainable AI, XAI. As neural networks have become more complex, the need for interpretable and transparent models has grown. Researchers are actively investigating ways to make neural networks more comprehensible to humans, enabling users to understand, trust, and effectively manage AI systems. The pursuit of XAI promotes the development of new neural network architectures and learning algorithms that maintain high performance while providing insights into their decision-making processes. AI research has also shaped neural networks through the rise of generative models, such as generative adversarial networks, GANs, and variational autoencoders, VAEs. These models have the ability to generate new data samples that are indistinguishable from real data. The implications of these capabilities are vast, from synthesizing realistic images and videos to drug discovery and personalized content generation. As generative models continue to mature, we can expect them to play a significant role in neural network research and applications. The integration of reinforcement learning with neural networks has ushered in a new class of AI known as deep reinforcement learning, DRL. DRL combines the perception abilities of deep neural networks with the decision-making capabilities of reinforcement learning. This integration has enabled breakthroughs in complex tasks such as playing video games at superhuman levels and improving robotics control systems. It is a field that continues to evolve, presenting novel opportunities for neural networks to learn and operate in dynamic environments. The expansion of neural network capabilities is further powered by advances in specialized hardware for AI computing, such as graphics processing units, GPUs, tensor processing units, TPUs, and other AI accelerators. These technologies provide the computational power necessary to train larger and more sophisticated neural network models. AI researchers and hardware manufacturers work in tandem to optimize neural network performance, leading to shorter training times and enabling the analysis of extensive, multifaceted datasets at unprecedented speeds. Beyond computational hardware, data itself is a driving force in the evolution of neural networks. The availability of vast amounts of data has been a catalyst for neural network breakthroughs. AI research now focuses on how to effectively handle and process big data, leading to neural network architectures that are more robust against overfitting and capable of extracting useful patterns from noisy, unstructured data. This focus includes the development of advanced data pre-processing techniques, data augmentation strategies, and unsupervised learning algorithms. Privacy and security are other crucial factors influenced by AI research in the neural network domain. With the increased use of neural networks in diverse fields, there is a growing need to develop secure and privacy-preserving AI systems. Techniques such as federated learning, where models are trained across multiple decentralized devices holding local data samples, have emerged in response. This method ensures data privacy and security while still benefiting from a collective learning process. Furthermore, the study of adversarial attacks and defenses is critical in designing neural networks that are resilient against malicious inputs designed to deceive AI models. The intersection of AI and neuroscience is also contributing to the evolution of neural networks. By drawing parallels between artificial and biological neural systems, researchers are uncovering new architectures and learning paradigms. This cross-disciplinary approach facilitates the development of neural networks that mimic aspects of human cognition, potentially leading to AI systems with enhanced learning efficiency and generalizability. The incorporation of theories from cognitive neuroscience into AI is expected to push neural network design beyond traditional computational limitations. Looking forward, the connection between AI research and neural network evolution will persist as a rich area of exploration. It is anticipated that future advancements will bring forth new paradigms that challenge our current understanding of neural networks and their capabilities. These developments will undoubtedly have profound implications across technology, science, and society. By continuing to align AI research objectives with emerging trends, the promise of neural networks to solve ever more complex problems becomes increasingly tangible. As we grow to comprehend the intricacies of artificial neural systems, the impact of this synergy on the landscape of AI will remain a dynamic and influential force. 10.2 Cross-disciplinary applications of neural networks. The exploration of neural networks has expanded beyond its roots in computer science and has started to have profound impacts across numerous fields. This fusion of disciplines is not just a matter of applying existing neural network techniques to new problems, but also involves the formation of fundamentally novel neural network architectures and learning paradigms inspired by the unique challenges and data structures present in these diverse areas of study. In this section, we explore the cross-disciplinary applications, considering how neural networks offer solutions to complex problems and how they are being tailored to fit the specific contours of various fields. In biology and medicine, neural networks are paving the way for remarkable advancements. For instance, in genomics, deep learning techniques are being used to identify patterns in genetic sequences that predict the onset of diseases, potentially leading to early diagnosis and personalized medicine strategies. In medical imaging, convolutional neural networks, CNNs, have become instrumental in enhancing image analysis, enabling the detection and classification of abnormalities in X-rays, MRIs, and CT scans with high accuracy, often surpassing the performance of seasoned radiologists. This transformation in the medical domain is driven not only by the inherent capability of neural networks to handle large datasets, but also by their ability to learn complex, nonlinear relationships inherent in biological data. In the realm of finance, neural networks are being used to predict market trends and assess risks, which are inherently complex and volatile. By learning from historical data, neural networks can capture patterns and dependencies that are not evident to human analysts. This capability allows for the creation of more robust models for quantitative trading, credit scoring, and fraud detection. Advanced recurrent neural networks, RNNs, like long short-term memory, LSTM networks, are particularly useful for these temporal data applications due to their ability to remember long sequences of past information, which is crucial for time series forecasting. In the field of environmental science, researchers are employing neural networks to model and predict climatic changes. The intricate relationships between different environmental factors such as temperature, precipitation, wind patterns, and more can be modeled through neural networks. These models are then used to simulate and forecast potential future climatic conditions, which is essential for planning and mitigating the impacts of climate change. This interdisciplinary approach calls for the integration of vast datasets and the expertise from both environmental scientists and data scientists to ensure that neural network models adequately represent the complex dynamics of Earth's climate. The utility of neural networks in the automotive industry, especially in the development of autonomous vehicles, cannot be overstated. Neural networks form the backbone of decision-making systems that allow vehicles to perceive their surroundings, interpret sensor data, and navigate through complex environments. These networks are not solely based on road scenarios and driving data, but also on cognitive models that help in understanding and predicting the behavior of other road users. The integration of neural networks into vehicles is a quintessential example of how cross-disciplinary research can yield transformative technological progress. In language processing, neural networks have spurred a revolution in natural language understanding and generation. Transformer-based models, such as BERT and GPT, are prime examples of neural architectures that have successfully captured the subtleties and complexities of human language. These networks have applications that range from real-time translation services to the creation of responsive chatbots and advanced text generation. This signifies a cross-pollination of computational linguistics, cognitive science, and machine learning, resulting in tools that can comprehend and interact in human language in unprecedented ways. The influence of neural networks is also seen in the creative industries. Generative adversarial networks, GANs, are being used to produce original artwork, compose music, and generate realistic animations. These networks have two parts: a generator that creates new content and a discriminator that evaluates the authenticity of this content. Through an adversarial process, the generator learns to produce outputs which the discriminator cannot distinguish from real-world examples. This approach encapsulates the creative process in a mathematical framework, thereby forging a new relationship between art and artificial intelligence. Agriculture is another sector reaping the benefits of neural networks. Precision farming, aided by AI, leverages data from various sources, including satellite imagery and ground sensors, to make informed decisions about planting, watering, and harvesting. Neural networks analyze this data to optimize crop yield, detect plant diseases, and reduce environmental impact. This application illustrates how technology can directly contribute to sustainability and resource management through intelligent data analysis. Neural networks are impacting the educational sector by enabling personalized learning experiences. Through detailed analysis of individual learning patterns, neural networks can customize content delivery, assess student performance, and provide tailored feedback. This personalized approach seeks to improve learning outcomes by adapting to the strengths and weaknesses of each student, which traditional one-size-fits-all educational methods often overlook. Finally, in the field of social sciences, there is growing interest in how neural networks can be used to analyze large-scale social patterns and predict societal trends. By processing data from social media, surveys, and economic indicators, neural networks can provide insights into public opinion, political dynamics, and collective behavior. These insights are invaluable for policymakers, sociologists, and economists who strive to understand and address complex social challenges. The cross-disciplinary applications of neural networks have only begun to scratch the surface of their potential. The integration of neural networks within varied domains continues to provide fresh perspectives, innovative solutions, and poses new questions regarding the capabilities and limitations of artificial intelligence. As we continue to explore these frontiers, the adaptability and evolution of neural network techniques will undoubtedly play a pivotal role in shaping future research trajectories and, by extension, the technological landscape. 10.3 The role of open source in neural network advancement. The open source movement has significantly influenced the advancement of neural networks by fostering a collaborative environment where individuals and organizations can contribute to collective research and development efforts. Open source provides access to a wealth of neural network frameworks, libraries, and tools, which reduces barriers to entry for both newcomers and experienced practitioners. It allows for the sharing of pre-trained models and datasets, which can be further enhanced or fine-tuned for various applications. This ecosystem has democratized access to state-of-the-art technologies, ensuring that the latest advancements are not confined to those with ample resources. The proliferation of open-source software has enabled a cumulative knowledge base that is larger than what any single entity could hope to achieve. As researchers and developers contribute to the refinement of neural network models and techniques, these contributions are vetted and validated by a global community. This results in the rapid identification and correction of bugs, the inclusion of diverse perspectives for improvement, and a pace of innovation that proprietary models often cannot match. Further, open-source projects come with extensive documentation and community support, which aids in understanding and utilization, thus accelerating the educational curve for neural network development. An essential aspect of open source is the transparency it brings to neural network development. Transparency is crucial for the verification of algorithms, the understanding of model behavior, and the assessment of potential biases within datasets. This openness leads to more reliable and trustworthy neural network applications, which is especially important in areas where decisions made by algorithmic models can have significant impacts. It allows scrutiny from the global community, encouraging ethical considerations and responsible AI development practices. Collaboration in open-source projects helps bridge the gap between academia and industry. Researchers can make their scientific contributions widely available, and industry professionals can adopt and adapt these innovations for commercial applications. This dynamic interaction facilitates the rapid transition from theoretical research to practical implementation, a key driver in the fast-paced development of neural networks. Also, as industries adopt open-source neural network software, they contribute back to the ecosystem by sharing real-world usage experiences and enhancements, which feed back into the research loop. Inclusion of diverse talent is another benefit of the open-source model. Since participants from around the world can contribute irrespective of their affiliation or location, there is a confluence of ideas that can stimulate innovative approaches to problem-solving. This diversity can also lead to more robust neural network systems that are tested across a wider range of environments and use cases, enhancing their generalizability. Different cultural and societal needs can be reflected in the work, which encourages the creation of more adaptable and flexible neural network solutions. Open-source platforms often serve as incubators for cutting-edge technologies in neural network development. As new theories and architectures emerge, they are frequently shared via open source before undergoing rigorous review and publication in academic journals. This means that state-of-the-art practices are disseminated quickly within the community, leading to a sort of real-time peer review. Such platforms can thus act as a litmus test for the viability and performance of novel approaches prior to their formal peer-reviewed publication. Open-source initiatives can also foster competitive spirit through organized challenges and competitions. These events leverage the community's creativity and are instrumental in solving complex problems. They often lead to groundbreaking solutions that can significantly advance the field of neural networks. As participants share their approaches and outcomes, there is a rich learning opportunity for observers. This aspect of collaboration and competition contributes to the rapid acceleration of neural network capabilities. Sustainability of neural network projects can be better ensured in the open-source context. Commercially driven projects can be shelved or restricted based on strategic shifts within a single organization. In contrast, open-source projects can continue to thrive even if original contributors move away or funding sources dry up, as the community can step in to maintain and continue the project. It creates a layer of resilience that is not always available with proprietary systems. Contributions to open-source projects often act as a form of peer recognition and can enhance an individual's or organization's prominence in the field of neural networks. Developers and scientists can showcase their expertise through meaningful contributions, which can lead to employment opportunities, collaborative ventures, or even commercial endeavors stemming from the project. This meritocratic aspect contributes to the development of high-quality, innovative neural network projects as it rewards talent and effort transparently. Open source has also contributed to the advancement of hardware required for neural network development. The open source ethos is not limited to software, it extends to hardware designs that can be shared and improved upon. With the resource-intensive nature of training neural networks, hardware optimizations and innovations are crucial for progress. Open-source hardware projects invite collaboration on neural network accelerators and other specialized processing units, driving advancements that help mitigate computational constraints. The future trajectory of neural network development will likely be shaped by contributions from the open-source community at an increasing pace. Integrated with other emerging trends such as automated machine learning, AutoML, reinforcement learning, and quantum computing, the open-source paradigm is set to play a critical role in shaping these technologies. It provides a foundation for integrating diverse methodologies, fostering interdisciplinary approaches, and ensuring that the neural networks of tomorrow are both powerful and accessible. As we move forward, the open-source community will continue to be a bedrock upon which the evolution of neural networks is built. 10.4 The rise of neuromorphic computing. Neuromorphic computing represents an interdisciplinary amalgamation of neuroscience, computer science, and electrical engineering, with the objective of developing computing systems that mimic the neurobiological architectures of the nervous system. At the core of neuromorphic engineering is the desire to transcend the limitations of traditional von Neumann computing architectures, which separate memory and processing units. This traditional architecture leads to a bottleneck known as the von Neumann bottleneck, where the speed and efficiency of computational systems are limited by the rate at which data can be transferred between the processor and memory. In contrast, neuromorphic systems seek to emulate the brain's highly parallel and distributed computational processes, potentially leading to more efficient and powerful computing systems. Fundamentally, neuromorphic systems are constructed with artificial neurons and synapses that aim to replicate the biophysical properties and functionalities of their biological counterparts. In such systems, the basic computational units are neurons, which communicate with one another via synapses. This is akin to biological brains, where neurons transmit signals through a complex network, forming the basis for learning and memory. Mimicking this dynamic allows neuromorphic computers to process information in a more natural and efficient way, dealing with complex, noisy, and dynamic data streams, much like the human brain does. The ascendancy of neuromorphic computing is facilitated by the development of novel materials and fabrication techniques that can create components mimicking the real-time plasticity of biological synapses. This plasticity refers to the ability of synapses to strengthen or weaken over time, depending on the level of activity in the brain, which is essential for learning and memory formation. Researchers are developing memristor technologies, among other technologies, that exhibit similar plasticity, thus paving the way for the implementation of learning algorithms in hardware that are fundamentally different from those in standard computers. Energy efficiency is another significant driver of neuromorphic computing research. The human brain operates on roughly 20 watts of power, a fraction of what modern supercomputers consume. Neuromorphic hardware seeks to approach nature's benchmark by dramatically reducing power consumption while performing complex computational tasks. This is accomplished through event-driven computation, where components activate only in response to stimuli rather than maintaining a continuous active state. This mirrors the energy-efficient nature of biological systems and has vast implications for mobile computing and devices that operate on limited power budgets. The real-world applications of neuromorphic computing are extensive and growing, including areas such as robotics, sensory processing, adaptive motor control, and sophisticated pattern recognition. In robotics, for example, neuromorphic systems could enable machines to process sensory information and adapt to their environment in real time, akin to living organisms. Similarly, In pattern recognition tasks, such as facial or voice recognition, neuromorphic computing has the potential to provide a substantial increase in speed and efficiency by performing computations in a way that is more aligned with the human brain's approach to these tasks. Despite the considerable promise, developing practical neuromorphic systems presents significant challenges. One of the primary hurdles is the complexity involved in designing and manufacturing synthetic neural networks that can simulate the broad functionality of the brain. As researchers work to increase the scale and capabilities of neuromorphic hardware, they must also address issues of connectivity and scalability, ensuring that increased system size does not result in prohibitively high power usage or loss of computational accuracy. Parallel to hardware developments, the rise of neuromorphic computing is driving innovations in neural network algorithms and software development. These advancements will be necessary to leverage the full potential of neuromorphic architectures. New learning algorithms are being formulated that can exploit the hardware's intrinsic properties, such as spike timing-dependent plasticity, STDP, which are distinctly divergent from algorithms used in conventional artificial neural networks. These algorithms are more suited to the asynchronous and spiking nature of neuromorphic hardware, and may give rise to new classes of artificial intelligence that more closely resemble biological intelligence in functionality. In bridging the gap between neuroscience and computing, neuromorphic systems also offer an unconventional platform for the study of the brain itself. By constructing systems that emulate brain processes, scientists can better understand the underlying principles of neural computations, potentially shedding light on cognitive processes and disorders. This cross-pollination between computing technology and brain research is leading to a more profound understanding of both domains, fostering a collaborative environment that benefits both fields. As we look towards the future, one can envision an ecosystem where neuromorphic computing plays a pivotal role in a new frontier of technology. Societal impacts could include the creation of more responsive and adaptive machines capable of complex decision-making and learning, reduced energy consumption across a variety of electronic systems, and novel approaches to problem-solving in computational science. Ensuring that neuromorphic computing develops in an ethical and secure fashion will be critical, particularly as its capabilities expand and it becomes more integrated into daily life. The quest to realize the full potential of neuromorphic computing is an evolving journey, with explorations into new materials, architectures, and computing paradigms. It is a journey marked by both the formidable challenge of emulating the intricate complexity of the human brain and the enticing prospect of unfolding an era of computing that could transform the technological landscape. As researchers and engineers forge ahead, they will undoubtedly continue to push the boundaries of what is possible, catalyzing breakthroughs that could redefine our relationship with technology and further blur the lines between biological and artificial intelligence. 10.5 Edge AI and the future of neural networks. The advancement of neural networks has historically been closely linked to the development of centralized computing resources, where data is sent to a central server for processing. However, this paradigm is shifting with the rise of Edge AI, which is the deployment of artificial intelligence algorithms on local devices at the edge of the network near the source of the data. This transition brings computational resources closer to where data originates, thus enabling faster response times, increased privacy, and reduced bandwidth requirements. Edge AI is inherently driven by the necessity to process massive amounts of data produced by devices such as smartphones, wearables, and IoT sensors. These devices generate data that can be sensitive or require real-time processing, making the transmission to a central server impractical. By processing data locally, Edge AI allows for real-time decision-making without the latency incurred by cloud-based systems. This is crucial for applications such as autonomous vehicles, where split-second decisions can be a matter of safety. In the context of neural networks, Edge AI represents a shift towards lightweight, efficient models that can operate within the constrained computational and power environments typical of edge devices. These models must be highly optimized to maintain performance while working with limited resources. Techniques such as model pruning, quantization, and binary neural networks are being developed to reduce the complexity and size of models without significant losses in accuracy. Additionally, federated learning has emerged as a novel approach that fits well with the edge AI paradigm. It allows for the decentralized training of neural networks across multiple devices, where each device trains a model locally with its own data and only shares model updates with a central server. This approach maintains data privacy, as the raw data never leaves the user's device, and also leverages the collective learning from multiple nodes, enhancing the robustness of neural networks. Training neural networks at the edge also poses unique challenges with respect to data distribution and availability. Devices at the edge often encounter data that is not identically distributed, which can lead to issues with model generalization. Additionally, the various devices may have different capabilities and resources, which necessitates adaptive neural network architectures that can cater to this diversity. Research into adaptive and scalable neural networks is therefore a critical aspect of edge AI. Moreover, the deployment of neural networks in edge computing requires careful consideration of security and privacy concerns. The distributed nature of these networks introduces new attack vectors that malicious entities could exploit. Secure and privacy-preserving protocols such as homomorphic encryption and secure multi-party computation are therefore integral to the advancement of edge AI to ensure that data and models are protected, particularly in sensitive applications. Edge AI also drives innovation in dedicated hardware optimized for on-device AI processing. Chip manufacturers are designing specialized processors that can efficiently run neural network computations on edge devices. These processors are typically designed to be power-efficient and capable of sustaining high computational workloads, which align with the needs of edge AI applications. The development of such hardware is vital to reduce the energy consumption and improve the performance of neural networks at the edge. One emerging trend facilitated by edge AI is the shift towards continuous learning, where neural network models update and adapt in real time as they are exposed to new data. This is opposed to the traditional approach, where models are periodically retrained in centralized data centers. Continuous learning on edge devices enables them to remain current and effective without the need to send data back to the cloud for retraining, thereby preserving data privacy and reducing network congestion. The integration of edge AI with other technological advancements, such as 5G and 6G wireless networks, further potentiates the capabilities of edge-based neural network applications. The high-speed and low-latency features of these next-generation networks will facilitate more complex AI tasks to be performed at the edge. This includes tasks that require significant coordination between devices, such as in smart city infrastructures and large-scale environmental monitoring systems. Lastly, edge AI is set to play a key role in democratizing access to AI technologies. By enabling AI processing on widely available devices without the need for high-end server infrastructure, it lowers the entry barrier for businesses and application developers. This will likely lead to a proliferation of innovative AI-powered applications tailored to specific needs and contexts, resulting in a more personalized and accessible AI experience for end users. The future evolution of neural networks will increasingly reflect the strengths and demands of the edge AI paradigm. As research in this domain continues to address its unique challenges, we can anticipate the development of increasingly sophisticated, efficient, and secure neural network models that are capable of operating autonomously on a vast range of edge devices, reshaping the landscape of AI application entirely. With these ongoing advancements, neural networks will become more intertwined with everyday processes and devices, extending their transformative impact on society and industry. 10.6 Neural networks in healthcare: opportunities and challenges. The advent of neural networks has significantly affected several industries, healthcare being one of the most impactful. Neural networks have introduced a paradigm shift in the ways we diagnose diseases, personalize treatments, manage patient data, and even conduct research into new medicines. As this technology continues to evolve, it promises to unlock unprecedented capabilities in healthcare, ranging from image-based diagnostics to predictive analytics. In diagnostics, neural networks have demonstrated exceptional performance, often surpassing human experts in accuracy. For instance, convolutional neural networks, CNNs, a class of deep learning models, have been successfully deployed in analyzing medical images such as X-rays, MRI scans, and CT scans. These networks can identify patterns invisible to the human eye, offering earlier detection of abnormalities which can be critical for conditions like cancer. By training on large datasets of medical images, these models learn to distinguish between benign and malignant tumors with high precision, thus aiding in the early stages of diagnosis. Beyond diagnostics, neural networks have also revolutionized treatment personalization. With the integration of patient data, including genetic information, neural networks can predict individual responses to treatments. This application is particularly transformative in fields like oncology, where intricate models can suggest the most effective drug combinations, reducing the trial-and-error approach in chemotherapy. These tailored treatments not only improve outcomes but also minimize potential side effects, optimizing the patient's quality of life. Patient data management is another area where neural networks bring substantial improvements. Electronic health records, EHRs, contain vast amounts of patient information that, when combined with neural networks, can lead to improved healthcare delivery. These networks can extract and synthesize information from the EHRs to alert healthcare providers about potential health risks, streamline care coordination, and support clinical decision-making. The ability to analyze vast datasets quickly means that care providers are informed by comprehensive, data-driven insights, leading to better health outcomes. Healthcare research has also gained a powerful tool through neural networks. In drug discovery, neural networks expedite the recognition of promising compounds by processing complex biological data. This reduces the time and cost involved in bringing new drugs to market. Moreover, in the age of precision medicine, neural networks contribute to understanding the complex interactions between genetics, environment, and lifestyle, helping to forge new paths in personalized medicine development. However, the integration of neural networks in healthcare is not without its challenges. One of the primary concerns is data privacy and security. Patient data is highly sensitive and bound by strict confidentiality laws like HIPAA in the United States. Ensuring that neural networks handling such data are secure against breaches and unauthorized access is paramount. Developers must implement robust security measures and encryption technologies to protect patient information and maintain trust in the healthcare system. Another significant challenge is the explainability of neural network decisions. Neural networks, especially those with deep architectures, often operate as black boxes, making it difficult to understand how they arrive at their conclusions. This lack of transparency can be a critical concern in healthcare, where the stakes of decisions are high. Clinicians need to understand and trust the outputs of neural networks to integrate them into their practice fully. Therefore, research into making these models more interpretable is crucial for their widespread adoption. The need for extensive and high-quality datasets to train neural networks poses another challenge. For these models to perform accurately, they require large volumes of diverse datasets that represent the full spectrum of human health conditions. Gathering such datasets is challenging due to a variety of factors including patient consent, data heterogeneity, and varying medical record standards across institutions. Efforts to standardize health data and promote data-sharing collaborations are essential to overcome these obstacles. Furthermore, there is a risk of bias in neural network models. If the training data is not representative of the broader population, the model may exhibit bias towards certain demographics. For instance, a neural network trained primarily on data from a particular ethnic group may not perform as well on others, which can lead to inequality in healthcare outcomes. It is vital to ensure that data used to train these models is as inclusive and representative as possible to avoid these biases. The increasing complexity of neural network models also demands a higher level of expertise, posing a challenge for their integration into healthcare. These models require specialists with knowledge in both machine learning and medicine to develop and maintain them. This intersection of skills is currently scarce, and the education system must adapt to produce professionals equipped to handle these specialized tasks. In terms of regulatory challenges, neural networks in healthcare present new territory for policymakers. Regulating these applications is complex due to the rapid pace of technological advancement and the difficulty of validating their efficacy and safety. Regulatory bodies like the FDA in the United States are developing frameworks to evaluate AI and machine learning-based software as medical devices, but there is still much work to be done to keep up with the innovation in the field. In conclusion, the incorporation of neural networks into healthcare promises enhanced diagnostic precision, personalized treatments, efficient data management, and accelerated research. The potential benefits are substantial, but so are the challenges, including ensuring data privacy, enhancing model transparency, acquiring quality training data, mitigating bias, cultivating specialized expertise, and navigating the regulatory landscape. As neural networks evolve, the healthcare industry must address these challenges through collaborative efforts between technologists, healthcare professionals, policymakers, and patients, thereby ensuring that this promising technology realizes its full potential to improve human health and well-being. 10.7 Neural Networks and the Internet of Things, IoT. The intersection of neural networks and the Internet of Things, IoT, is heralding a new frontier in technological innovation. The IoT ecosystem, comprising a vast network of interconnected devices, generates enormous quantities of data that can be overwhelming for conventional data processing techniques. Neural networks offer a powerful tool for sifting through this torrent of information, recognizing patterns, and making decisions with little to no human interference. This potential is best understood within the context of advancements in both fields and the unique benefits their convergence brings. A neural network is essentially a computational model inspired by the structure and functions of the human brain. It consists of interconnected processing nodes or neurons, which are programmed to recognize complex patterns and relationships in data. When applied to IoT, these neural networks can process and analyze data from myriad sensors and devices, enabling sophisticated automation and predictive maintenance. The IoT, in turn, provides a real-time data-rich environment in which neural networks can continually learn and improve, optimizing their performance in tasks such as anomaly detection, system optimization, and resource management. For instance, in smart homes, neural networks can learn from the way lighting, heating, and appliances are used, making adjustments over time to conserve energy and improve efficiency. This is achieved through the continuous streaming of data from IoT sensors throughout the home, which provides the neural network with the necessary information to understand usage patterns and predict future needs. The use of neural networks in this context is not just for convenience, it also has significant implications for energy conservation and sustainability. In industrial settings, neural networks and IoT are revolutionizing predictive maintenance. By predicting equipment failure before it occurs, companies can save on costly repairs and downtime. IoT devices equipped with various sensors collect real-time data on machinery performance, which neural networks analyze to detect anomalies that precede equipment failure. These networks are trained on historical data and can evolve their understanding of what normal operation looks like, thereby improving their predictive accuracy over time. In healthcare, IoT devices can monitor patients' vital signs continuously, and neural networks can process this data to provide insights into the patient's health status. This has the potential to transform remote patient monitoring, where neural networks can identify deteriorating conditions before they become life-threatening and alert healthcare providers, allowing for prompt intervention. The advantage of using neural networks in this instance is their ability to recognize complex patterns in the data that might not be immediately evident to human observers. Regarding security, both IoT and neural networks play critical roles. IoT devices can be vulnerable to attacks, creating the need for robust security mechanisms. Neural networks can assist by constantly monitoring network traffic to detect unusual behavior that could indicate a security breach. Unlike traditional security systems, neural networks can adapt to new threats as they emerge by learning from past intrusions, making IoT networks more resilient to cyber attacks. The integration of neural networks and IoT also paves the way for advanced robotics. Robots equipped with IoT sensors can gather data about their environment and feed it into neural networks, which then help the robots to navigate, make decisions, and perform tasks autonomously. This symbiosis can be applied in various contexts, from manufacturing floors to exploration in hazardous environments, delivering efficiency and minimizing human exposure to danger. In the realm of agriculture, IoT sensors deployed in fields can measure factors such as soil moisture, crop health, and weather conditions. Neural networks can analyze these data streams to facilitate decisions on planting, irrigation, and harvesting, optimizing yields and reducing waste. The ability to predict the best times for sowing seeds or applying fertilizers, based on deep learning algorithms, exemplifies the integration of domain expertise with advanced data analytics. A further implication of the combination of neural networks and IoT lies in urban planning and smart city initiatives. IoT can help monitor traffic flows, pollution levels, and public infrastructure usage, while neural networks can process this data to enhance city management. By predicting traffic congestion or energy requirements, cities can optimize resource allocation, improve traffic routing, thereby enhancing the quality of life for residents. In retail, neural networks powered by IoT data can provide personalized shopping experiences. Based on customer interactions with IoT-enabled devices, such as smart shelves and carts, neural networks can tailor recommendations and offers in real time, creating opportunities for targeted marketing and improved customer service. Retailers can optimize inventory management, reduce costs, and enhance the overall shopping experience as neural networks provide insights into buyer behavior. Finally, as neural networks and IoT evolve, so do the challenges that need to be addressed. Among the most pressing are data privacy and ethical concerns regarding automation and decision-making. As devices become more pervasive and neural networks more autonomous, ensuring that personal data is handled securely and that automated systems are transparent in their decision-making processes becomes crucial. Researchers and practitioners in the field are continually developing new approaches to address these challenges, seeking to ensure that these technologies benefit society while safeguarding individual rights. The convergence of neural networks with the growing expanse of IoT devices represents a synergy that is only just beginning to be tapped. The immense potential of neural networks to bring intelligent analysis and decision-making to the vast data generated by the IoT will continue to spawn innovations across various sectors. With each improvement in neural network algorithms and the expansion of IoT infrastructure, new applications and opportunities will emerge, shaping a future where smart, interconnected systems augment human capabilities and lead to more efficient, responsive, and intelligent environments. 10.8 The convergence of AI and blockchain. The integration of artificial intelligence, AI, and blockchain technology represents a significant development in the computational and data science arenas. One of the primary emerging trends in this domain is the enhancement of data security and integrity through decentralized ledger systems. Blockchain technology offers a high level of security by storing data across a network of computers, making it tamper-resistant. By coupling this with AI, which requires a substantial amount of data for machine learning processes, the combined technologies can potentially create a more robust and secure environment for managing sensitive information. AI systems benefit greatly from large datasets, which are essential for the training and development of accurate models. However, the collection and storage of vast quantities of data raise concerns over privacy and security. Blockchain technology addresses these concerns through its inherent design that ensures transparency and immutability of records. Each transaction on the blockchain is recorded and time-stamped, offering a verifiable and auditable trail. The integration with AI means that not only is data secured, but it is also processed and utilized effectively, leveraging blockchain's traceability to increase trust in AI-based systems. In the context of smart contracts, the convergence of AI and blockchain is particularly significant. Smart contracts are self-executing contracts with the terms of the agreement between buyer and seller directly written into code. They run on a blockchain and automatically enforce and execute contract terms. The incorporation of AI into smart contracts can introduce dynamic decision-making capabilities that adapt to new information or conditions, without the need for human intervention. This combination promises to streamline complex business processes and reduce the potential for disputes or misinterpretation of contract terms. Another key area of convergence is the advancement of decentralized autonomous organizations, DAOs. These are organizations that are run through rules encoded as computer programs that are transparent and controlled by organization members rather than a central government. AI can play a crucial role in the management of DAOs by facilitating decision-making and automating administrative tasks, which can result in increased efficiency and reduced human error. These AI-driven DAOs could potentially operate with minimal human oversight, as the AI systems could be tasked with optimizing operational efficiency based on real-time data and predefined objectives. The field of data marketplaces is also undergoing transformations due to the synergy between AI and blockchain. Data marketplaces enable the buying and selling of data in a secure and transparent manner, which is essential for feeding the ever-growing appetite of AI systems for new data. Blockchain provides the framework for such transactions to occur securely and immutably, while AI can be used to analyze the data and ensure its quality and relevance. This can increase the value of the data being traded and ensure that it meets the specific needs of the buyers, driving innovation in various sectors. One nascent yet promising trend is the use of blockchain to track and manage the intellectual property rights of AI algorithms and datasets. As AI models become more complex and valuable, ensuring the ownership and proper usage of these digital assets is paramount. Blockchain can provide an indisputable record of ownership and licensing agreements, enabling the creators of AI algorithms to monetize their work while preventing unauthorized use. This is essential to fostering both innovation and fairness in the AI development community. In the realm of cybersecurity, the convergence of AI and blockchain is being leveraged to create more resilient systems against attacks. AI can monitor blockchain networks for unusual patterns that may indicate a security threat, such as a 51% attack in which a user or group gains control of the majority of mining power. Simultaneously, blockchain can store tamper-proof records of AI behavior, which is crucial for auditing AI decisions and operations post-breach. This dual strategy enhances both the detection of security incidents and the forensic analysis following an attack. Additionally, AI algorithms can optimize the operations of blockchain networks, improving performance and scalability. The computational overhead of maintaining a blockchain, particularly with proof-of-work consensus mechanisms, is significant. AI can be employed to find the most efficient ways to carry out the mining process, or to develop alternative consensus mechanisms that consume less energy and resources. This would enable blockchains to scale up and accommodate more users without compromising speed and security. The fusion of AI and blockchain is also gaining traction in the supply chain and logistics industry. Blockchain provides a reliable way to document the provenance and journey of goods, preventing fraud and ensuring compliance with standards. AI enhances this by predicting supply and demand, optimizing routes, and managing inventory through data analysis. The real-time insights generated through AI can dynamically adjust supply chain actions, leading to a more agile and responsive system. This is especially important in a global economy where supply chains are increasingly complex and subject to disruption. Furthermore, the intersection of AI and blockchain has implications for the labor market and the gig economy. Blockchain-based platforms can ensure transparent and fair compensation for freelancers and gig workers, while AI can match these workers with optimal opportunities based on their skills and previous performance. This could lead to an ecosystem where individual contributions are more accurately valued and rewarded, and where the alignment of tasks with skill sets is improved. This enhancement of the gig economy could have widespread social implications, including more flexible work arrangements and improved job satisfaction. Finally, the convergence of AI and blockchain is facilitating the emergence of new governance models. By using AI to analyze human sentiments and blockchain to create immutable voting records, these technologies can provide more responsive and transparent governance systems. AI can help to synthesize public opinion by analyzing social media data, and blockchain can secure citizen votes, leading to potentially more democratic and efficient decision-making. This marriage of technologies can not only transform business operations, but can also have a profound impact on the social and political fabric of society. The burgeoning synergy of AI and blockchain is a clear marker of an emerging paradigm shift in technology. Notably, while the blending of these two technologies holds great promise, there are significant challenges to overcome, such as interoperability issues, the complexity of integration, and regulatory hurdles. The distributed nature of blockchain and the centralized nature of most AI computing structures must find a harmonious balance that capitalizes on the strengths of both while mitigating their weaknesses. Nonetheless, as these technologies continue to evolve, we can anticipate significant advancements that may well redefine the landscape of modern computing and digital transactions. The convergence of AI and blockchain has the potential not only to revolutionize industries, but also to fundamentally alter the way in which we trust, interact with, and benefit from technological systems. 10.9 Ethical AI and Neural Networks. As the integration of artificial intelligence, AI, into society deepens, understanding and addressing the ethical implications of this technology, especially in the context of neural networks, becomes increasingly important. Neural networks, which are inspired by the biological neural networks of the human brain, are a subset of machine learning algorithms central to many AI systems. Their ability to identify patterns and make decisions by processing complex datasets can lead to significant societal changes, which raises various ethical concerns. The relevance of ethical considerations in AI resides not only in the potential for new forms of social impact, but also in the urgency posed by the accelerated pace of technological innovation. One of the primary ethical considerations related to neural networks is data privacy. Neural networks require vast amounts of data to learn and make predictions. Often this data is of a personal nature, collected either directly or indirectly from individuals. Ensuring that such data is utilized in a manner that respects individual privacy rights is essential. This involves not only the ethical treatment of data, but also consideration of the methods by which it is collected, stored, shared, and destroyed. Regulations like the General Data Protection Regulation, GDPR, in the European Union have set a benchmark for data protection, reflecting growing concerns over data privacy and providing a framework for AI ethics. Bias and fairness in AI systems are also major ethical concerns, as neural networks can inadvertently learn and amplify societal biases present in their training data. If not carefully designed and reviewed, AI systems can perpetuate discrimination based on race, gender, age, or other protected characteristics. Bias in training datasets can result from a lack of diversity in the data itself or from historical inequalities and prejudices. As a result, neural networks may produce biased outputs, leading to unfair treatment of individuals or groups. Combating this requires careful dataset curation, continual assessment of AI decision-making, and the development of methods to detect and correct bias. Accountability and transparency of AI systems, particularly those using neural networks, are fundamental to ethical AI. As neural networks become more complex, understanding how they arrive at specific decisions can be challenging. This opacity is often referred to as the black box problem. When a neural network makes a decision, such as approving a loan application or diagnosing a disease, stakeholders need to understand the basis for the decision. Developing techniques that enable humans to interpret neural network decisions, such as explainable AI, XAI, is critical to ensuring accountability and trust in AI systems. The automation and decision-making powers granted to neural networks bring into question the ethics of autonomy and consent. As AI systems automate tasks traditionally performed by humans, questions arise about the extent to which these systems should act autonomously. There must be safeguards to ensure that neural networks do not make unsupervised decisions that could have negative consequences. Moreover, individuals should have the right to understand when and how AI is making decisions that affect them, along with the capacity to opt out or challenge these decisions. Issues surrounding the use of AI and neural networks for surveillance and control are of particular ethical concern, as they intersect with civil liberties and human rights. AI-powered surveillance systems can enhance security, but they can also erode privacy and enable mass surveillance. The potential for misuse by governments or corporations underscores the need for clear ethical guidelines and mechanisms of oversight to govern the use of neural networks in surveillance applications. The future deployment of neural networks in autonomous systems, such as self-driving cars or autonomous weapons, poses ethical challenges that society is only beginning to contemplate. These systems require careful ethical considerations regarding responsibility if something goes wrong. Determining whether the manufacturer, the operator, or the neural network itself, insofar as it makes independent decisions, is responsible for unintended outcomes is a complex issue that must be addressed. As we consider the global reach of AI, equity and access become ethical concerns associated with neural networks. The advantages conferred by AI could lead to the exacerbation of inequality if access to technology remains uneven around the world. There must be a concerted effort to ensure that the benefits of neural networks are accessible to all segments of society, and that these technologies do not deepen the digital divide. The development of international standards and regulations for AI ethics is an evolving process. Recognizing the importance of ethical AI, many countries and international organizations are working to create frameworks and guidelines. These efforts include the establishment of ethical principles for AI, regulatory measures, and cooperative agreements between nations. The aim is to create a consensus on the best practices for developing, deploying, and governing neural networks in a manner that respects human rights, promotes societal well-being, and ensures security and peace. As neural networks become more advanced, there must be a parallel evolution in the ethical frameworks that guide their use. Ethical AI research is a multidisciplinary field that draws from philosophy, law, computer science, and social sciences to address these challenges. To keep pace with technological advancement, ongoing research and dialogue are necessary to anticipate future ethical dilemmas. The effective governance of neural networks requires not only an understanding of the technology, but also a proactive approach to the multitude of ethical questions it engenders. Ethical considerations in AI and neural networks will continue to be an area of significant importance as these technologies further integrate with everyday life. The development of policies that encourage ethical AI practices is vital for fostering an environment where neural networks contribute positively to society. It also requires collaboration between policymakers, technologists, ethicists, and the public. By remaining vigilant and responsive to the ethical challenges posed by neural networks, society can harness the benefits of AI while mitigating its risks and ensuring that AI technology evolves in concert with our shared values and principles. 10.10 Predictions for the next decade of neural networks. The field of neural networks has been a major force behind numerous advancements in artificial intelligence, AI, over the past decade. As we look to the future, it is expected that neural networks will continue to evolve, leading to new capabilities and applications that will shape various aspects of technology and society. This chapter delves into the potential developments and transformations we can anticipate in the realm of neural networks over the next 10 years. One potential advancement is the increased sophistication of neural network architectures. Current popular models like convolutional neural networks, CNNs, and recurrent neural networks, RNNs, are likely to see significant modifications that enhance their performance and efficiency. As research in this area progresses, we may witness the emergence of new architectures that blend the best aspects of existing models in innovative ways. Such hybrid architectures could offer greater accuracy and speed, allowing neural networks to solve more complex problems with less computational power. Another prediction for the coming decade is the further integration of neural networks with quantum computing. While still in its infancy, the intersection of quantum computing and neural networks, known as quantum neural networks, holds promise for tackling tasks that are currently infeasible for classical computers. Quantum neural networks may be able to process information at significantly faster rates and handle problems involving vast amounts of data, such as simulating complex biological processes or optimizing large-scale logistics operations. The explainability and transparency of neural networks are likely to become a major focus in the near future. As these systems are increasingly applied to critical areas like healthcare, finance, and autonomous vehicles, understanding how neural networks make decisions becomes crucial. Efforts to develop techniques for visualizing and interpreting neural network decision-making processes will progress, leading to more trust and wider adoption of these technologies across sensitive sectors. Data privacy concerns are also expected to drive innovation in neural network training methodologies. Techniques like federated learning, which allows for model training on decentralized data, are set to become more widespread. This approach will enable neural networks to learn from data that is kept on users' devices, minimizing the risk of privacy breaches. Additionally, advances in synthetic data generation may provide a way for neural networks to be trained on rich datasets without compromising user privacy. The scalability of neural networks will see marked improvements, making it feasible to deploy these models in edge computing devices such as smartphones, smart sensors, and IoT devices. The development of lightweight and efficient neural networks that can run on low-power hardware will contribute to the growth of intelligent applications at the edge of the network, reducing the reliance on cloud-based AI services and allowing real-time processing and decision-making. The field of reinforcement learning, RL, which involves training neural networks through trial and error using rewards, is set to gain prominence as researchers explore more sophisticated RL algorithms. These advancements will likely lead to breakthroughs in autonomous systems, where machines can learn and adapt to new environments and tasks without human intervention. The application of reinforcement learning could extend beyond robotics to areas such as energy management, traffic control, and personalized education. Custom hardware tailored specifically for neural network computations, such as application-specific integrated circuits, ASICs, and field programmable gate arrays, FPGAs, will become more prevalent. As the demands for processing neural network workloads continue to grow, the development of specialized hardware accelerators will be prioritized to provide the computational efficiency and speed required. This specialized hardware will play a key role in enabling neural networks to be deployed in a wider array of devices and applications. The interplay between neural networks and the field of genetics is another area that holds significant potential. By using neural networks to analyze genetic data, researchers aim to unlock new insights into complex biological processes and diseases. This partnership between computational models and genetics can drive progress in personalized medicine, where treatments and preventive measures can be tailored to an individual's genetic profile. Multimodal neural networks that can process and draw inferences from various types of data, such as text, images, and sound, are likely to advance. By combining modalities, these networks can achieve a more comprehensive understanding of the world, akin to natural human perception. Such multimodal systems could revolutionize fields like content creation, surveillance, and multilingual communication by enabling more context-aware interpretations and responses. Lastly, the democratization of neural network technologies will play a pivotal role in the coming decade. As tools and platforms for developing and deploying neural networks become more user-friendly and accessible, a broader range of individuals and organizations will be able to leverage these powerful models. Open-source libraries and cloud-based AI services will lower the barriers to entry, fostering innovation and allowing a diverse set of stakeholders to contribute to the advancement of neural network applications. The predictions outlined in this section provide a glimpse into the potentially transformative impact of neural networks in the next decade. As researchers, developers, and businesses continue to push the limits of what neural networks can achieve, it is clear that these advancements will not only enrich the field of AI, but also permeate ever more deeply into our daily lives, redefining what is possible with technology. Conclusion. As we reach the conclusion of neural networks, we stand at the threshold of a new era in artificial intelligence. This journey through the world of neural networks has not only illuminated the depth and breadth of this field, but also underscored its dynamic and transformative nature. Throughout this book, we have traversed the historical pathways that led to the development of neural networks, explored the intricate workings of their architectures, and witnessed their profound impact across various domains. From the basic structures of neurons and synapses to the complex designs of deep learning models, each chapter has contributed to a comprehensive understanding of neural network technologies. The discussions on specialized neural network models and their applications in fields like healthcare, finance, and autonomous systems highlight the versatility and adaptability of these tools. The exploration into advanced topics, including quantum neural networks and neuromorphic computing, has opened windows to future possibilities that may redefine what machines are capable of achieving. As we have seen, neural networks are not without challenges. Issues such as ethical considerations, bias, and the need for explainability in AI decision-making processes are critical areas that require ongoing attention and thoughtful solutions. The convergence of AI with other technologies, such as blockchain and the Internet of Things, further expands the horizon of opportunities and challenges alike. In closing, neural network is more than a summation of current knowledge. It is an invitation to continue exploring, experimenting, and innovating. The future of neural networks is not set in stone. It is a narrative that each researcher, practitioner, and enthusiast contributes to. This book lays the foundation, but the journey forward is a collective endeavor that will shape the future of AI and, in turn, the future of our world. The neural network revolution is just beginning, and its trajectory will be shaped by the curious minds and skilled hands of those who dare to dream and innovate. May this book serve as both a guide and an inspiration for all who seek to partake in this exciting journey.